Hello. Please notify me if you can hear me and see the screen and my drawing. Please write in chat if you can hear me and see my screen. It's new experience for me. It's all good? Great. Okay, I will start soon. If you have any questions, write them in chat. After I finish going through the explanation, or like some part of explanation for harder problems, if there will be like several steps, I will look at the chat and try to answer some questions. Can I be more loud? Let's see. I can try to bring the microphone closer. Is that better? Okay, I will just try to speak with my normal volume, like when I'm just sitting in the room and recording a video, it's hard to talk loud because there is nobody here. How was your Christmas? Yeah, it was fine, chill. We just watched some movies and played some games with my wife. Nice, chill Christmas. All right, I think we should start. We'll start with problem A. Problem A, we were given three integers L, R, and X, and wanted to calculate the number of pairs AB such that A is not greater than B and they both lie in the segment from L to R, and their average is equal to X. That's a easy problem, as it should be for problem A. So we have left border, have right border, have X somewhere. It can be outside of the segment. It's an important case that we will need to consider, but like the interesting case when we need to actually calculate something is when X is on the segment. So our average must be X. It means that basically A and B must be on the same distance from X on different sides, right? And since A should be at most B, it means that B is on the right and A is on the left, except in the case when they're both equal to X. And we can see that basically we want to calculate the number of ways to choose this distance, and A and B should both be on the segment, so we can calculate what is the maximum value of this distance, like to the left, so that A is still on the segment. So L should be at least x minus d, and on the right R should be at least x plus d. And from here we get that d should be at most x minus L, and also d should be at most r minus x. And then we just count the number of non-negative integer values of d that satisfy this, which will be minimum of those values plus 1, except if one of those values is negative, which means that x lies outside the segment, then there are no ways, so we just print 0. That's it for problem A. Are there any questions about problem A? While I'm waiting and giving you time to ask questions, I'll remind myself the statement of problem B. Okay, I don't see any questions, so we will move on to problem B. In problem B, we were given an array, and then we will remove all elements but one. And we are given number k such that k times we must take one element, like we are choosing a pair of consecutive elements, and k times we must delete the left one, and n minus 1 minus k times we must delete the right one. And we asked what is the maximal remaining element we can achieve. So we just want to determine which positions we can be left with. So let's say that we want to take this position and keep it and remove everything else. How can we achieve that? Well, obviously we don't want to do operations that remove this position. And if we have something on the left, there must be at least one operation that removes the left element in the pair, because like we can try to make this part smaller, but when we will be left with one element, we cannot remove it on its own. We need to pair it with this element that we cannot touch, so we will have to remove the left one element in the pair at least once. So if there is something on the left, we need to remove the left element at least once. And the same will be true for the right side. If there is something on the right from the element that we want to keep, we will have to remove the right element in the pair at least once. So if k is 0, so we can never remove the left element, then it's clear that we will keep the leftmost element, and this shows that nothing else is possible. If we want to keep not the leftmost element, then we have to remove something on the left at least once, but we cannot because k is 1. So the answer will be just a 1. Symmetrically, if k is n minus 1, then we will keep the rightmost element, and we cannot keep not the rightmost element. But if k is between those two, then both those conditions are satisfied, and well, at least those conditions do not prohibit us from doing anything, and we can see that actually we can achieve any element. If we want to keep some particular element, let's just keep one operation that will remove the last element on the left, keep one operation that will remove last element on the right, if there are any, and then like take those left and right halves and trim them by like choosing two consecutive elements in one half and removing any one of them just with which operations we have left. So we kind of set aside operations that we will need to remove one element on the left and on the right from us, and then kill everything that is everything except one element on the left and everything except one element on the right with any operations that we have. So if both those cases are not true, then we can just keep any element. So the answer is just maximum in the array. Any questions about problem B? Is the stream still working? It's very junky for in my preview, but it says that the quality is good. So I'm hoping that you still didn't lose me. I'm still here. And I don't see any questions in the chat about problem B. I'll give it another minute while I'm reading C, and then if there are still no questions, we'll move on to problem C. Well, I don't see any questions, so problem C. We have n children standing in a row, and each child has two numbers, AI and BI. For each child, we need to decide how many gifts we will give them. And on those GI, we have some conditions. For every child GI is at least AI. And also for each child, they cannot have less than what their neighbor has minus BI. And the same for the left neighbor. So those should be satisfied, and we want to minimize the sum of gi. Right, so this problem can be actually solved greedily. Kind of just give, so for every child, they must get at least AI. So let's start by kind of giving them AI already. And then if we have some unsatisfied children, let's increase their number of gifts until they're satisfied. And basically we will increase like by one every time. And at some point, everyone will be satisfied. And like we can see that all the gifts we have given, they must have been given, because otherwise there will be a child that is not satisfied. Because if there is a child that is not satisfied right now, we cannot improve their mood by not giving them more gifts. So we have to increase their value. But that's like very high level and not clear how to implement. You could try to like maintain some kind of queue of events that you need to proceed when we have some unhappy child. Put their index in queue and then process those events. When we give some child more gifts, maybe some of their neighbors become unsatisfied, and we check that and put them in queue if needed. That will work, and it will work in O of n actually, but it is not easy to understand why there wouldn't be a long sequence of like creating new events and then giving more gifts that will create new events and so on. I mean, there can be such long sequences, but the total number of events will be linear. Oh, hi Alexander, please elaborate on the queue sync. Right, so I can certainly choose an order where I do n square operations. Yeah, probably. Yeah, you're probably correct. Sorry, disregard that will not work in linear number of operations. But so the problem, like, why is that slow? Because we are doing updates in like arbitrary order. So like, we can create more events than needed. But actually what we can do is go from left to right once and do the updates. So we start by assigning GI to AI, then we go left to right and update each element. If this is GI, we can update GI plus 1 with max equal GI minus BI plus 1. Do that one from left to right. And then do similar for from right to left, updating gi with gi plus 1. So gi is max equal gi plus 1 minus bi. And after we do those two first, actually we are done. Every child will be satisfied after that. And that is true because all of our bi are non-negative. So when we push some limitation from left to right, it cannot go back, because like each time we go by an edge, our the number of gifts we want decreases. So like we cannot go to the right and go to the left and like create some greater limitation that is not yet satisfied. So we only need to push all of them once from left to right and from right to left. What's important is that like the updates from left one to the right one are done in the sequential order from left to right, because there can be like some guy here who imposes a restriction on a guy on the right through like this sequence of steps to the right. We cannot do steps in both directions because like that doesn't provide stricter restrictions, but we can have a long chain of restrictions that moves in one direction. So to process all those chains, we just go from left to right once and then from right to left once, and that's it. The solution is linear in N. Any questions about problem C? So the problem with streams is that I cannot see your eyes and hands and body language to understand if you're understanding everything or not understanding anything. So please write in chat if everything is clear and we should move on, or you have some questions about problem C. There was also a question when the random winners will be determined. I don't know. I'm just an invited analysis. I don't participate in prize giving other than as a receiver. Yay. More news. All right. If there are no questions, then we will move on to problem D. Actually, yeah, sending like hearts, reactions, and stuff like that is a good way to show that like I understood the solution. We can move on. You don't need to write anything. Just send the reaction, and I will see that there is a person that understood something. Okay, problem D. That one was actually hard for me. Stumbled on this one. There is a question that I don't understand. Do you think much during contest, or just if it works then move on? I don't understand the question. Well, I think enough to solve the problem. Sometimes I don't think enough to solve the problem, and the problem is not solved. If I solve the problem, then I move on. If I don't solve the problem, I keep trying, or sometimes I don't keep trying. You probably want to ask like if I prove the solutions. Well, I try to most of the time. Sometimes some belief is needed. In problem C, for example, it is kind of a well-known type of problem. I just know that it works, so I don't have to think about proving stuff. It's just I have seen it before. But yeah, generally I try to prove my solutions. Okay, let's move on to problem D. In problem D, we were given an undirected graph with most 5,000 vertices and most 5,000 edges. We want to count the number of ways, to remove some set of edges. Such that after that the graph is good. What does it mean that the graph is good? The graph is good if we can choose an order order of edges for every order of adjacent edges for every vertex, like order in which we consider neighbors for every vertex. Can choose an order of neighbors, so that if we run a DFS from vertex 1, then the order in which we visit the vertices will be 1, 2, 3, and so on. And so all the vertices will be visited in increasing order. So first, let's try to understand how to check if the graph is good. Like, let's say that we have fixed which edges we want to remove, so we have some edges left. How do we check if there is such an order of neighbors that DFS from vertex 1 visits all vertices in correct order? One way to think about it is actually, if there is an order of neighbors that works, we can just sort neighbors in every vertex. Why is that? Well, the idea is that if we are on the right track, it means that at any moment we will have like this prefix of vertices visited. So some vertices up to m are visited, and then all of those are not visited. Let's say we are staying at some vertex v. It should be in the visited part, obviously. We have already considered some edges from it, but obviously all of those edges were leading to this prefix. Because if we consider an edge to a not yet visited vertex, we just use it. So some of the edges to this prefix are considered. There might be some other edges from vertex v. Some of them will still go to this prefix, and some of them will go to the unvisited suffix. If we look at the edges to the visited part, it doesn't change anything. If we look at the edge and like the neighbor was visited, we don't do anything in DFS. So we might as well do it right now. So like if when we're staying at this vertex and we have this visited prefix of vertices, we can make sure that we have already considered all the edges to this prefix. Then if we have more edges that go to the suffix, if we consider one of them, and we must do it, we must consider one of the edges, because like in DFS, when we're staying in the vertex, we will consider all the edges from that vertex eventually. So we have tried edges to the prefix, used some of them, didn't use the others, but all of them are considered now. If we have some more edges to consider that go to the suffix, the next one we will use, so we will traverse in DFS. And the next vertex we must visit is m+1, otherwise our order is wrong. So among all of those edges to the suffix, we can only use the edge to m+1 right now. And like, what is so special about m+1? It is the smallest number on this unvisited suffix. So basically, I have shown that at any moment you should try to use edge with the smallest number, like with the smallest neighbor, which is just sort neighbors in every vertex. Okay, great. So that's just nice to know, because we can sort the neighbors right away before removing any edges, and then decide which to remove. We will just like pick them out of that sorted order, but the neighbors that are remaining will stay in the same sorted order. Okay, now let's look at our DFS tree that we are trying to construct. So 1 is the root. Then from 1 we must visit vertex number 2. From 2 we will visit something, maybe. If we visit something, then we must go to 3, then something here. Then there will be some bigger vertex here. Then, for example, we stop in 2. I don't know, let's say that this vertex is 9. Then from 1, the next vertex will be 10. And so on. Um, so this should be our DFS order, and we can see that every subtree in the in our DFS tree must be a subsegment of the DFS order. And let's say that the segment is from L to R, then L is the root of the subtree. Great. So okay, I don't think I have natural explanation for why we will do this, other than like we have looked at this subtree and not looked at the tree structure, not just that subtree is a segment. So we will try to do a subsegment DP. We will try to calculate DP LR, number of ways to do something. We will see like at which moment we are deciding on which edges we are removing. But like this will be a number of ways to do some of the choices, such that segment LR is a subtree with root L in the DFS tree. And how can our transitions look like? For simplicity, let's just say that for now we just want to calculate how many different DFS trees there are. Like ignore for now that we are counting the number of ways to remove the edges. Because we just want to understand the DP structure, and then we will like define exactly what we are counting, so that in the end we count what we need. So how can we build a subtree with like that covers this segment? Actually, we will like this DP will be slightly different. Okay, I guess for the purposes of explaining, let's say that like okay, so this DP is not number of full subtrees. Let's call it T. Okay, so this will be the number of trees, and we will also have like DP for like not full subtrees. Like we have added something, but we might add more sons to the root later. So like this will be F R. So actually T is just F. Like at any moment we can just choose to stop adding new subtrees. So those are actually just equal. But for the purposes of explanation, we will say that they're different. So laggy. I don't really know what I can do about it. Um, um, I have tried to change some settings. Does it make it better? Okay, so I guess reducing the bitrate did something good. Okay. It's relatively working, right? Can you please confirm that it is working? Or it's not working? I don't know. Okay, YouTube Studio says that stream health is excellent now. So I will continue the explanation. Right, so where were we? We are doing subsegment DP. TLR is number of ways to do something, so that the segment from L to R is subtree rooted at L, and FLR is the same thing, but like we're kind of expecting that we will add more children to the root. But actually T is the same as F, because like if we have some way to cover the segment LR with the root in L, we can just stop adding children, so the number of ways to do a tree is the same as number of ways to do it, like not a full tree. But now, how do we update F? So the base values are obviously just FLL is 1. If we have one vertex, it is not a full subtree. And now if we have some tree LR, then if we want to add the next edge, this one, so R was like the last visited vertex here, then this one must be R plus 1. Right? So we must have the edge from L to R plus 1. And then we are choosing some subtree here that ends somewhere, ends the tags. So if we have this edge from L to R plus 1, then we can do the transition, and there is like not non-full tree that the root is still L and the last vertex X. So we add here the number of non-full trees from L to R multiplied by number of trees with root R plus 1 that cover everything up to X. Is it lagging again? Yeah, I think it's not working. Bum, bum, bum. Yeah, I asked it like a minute ago, so I guess it is lagging very hard. Okay, I will try to reduce even more. Maybe I have some too, too high resolution or something. Okay, let's continue and hope for the best. So the last thing I did was to explain the transition. When we want to add a new subtree, we need to we need to make sure that this edge exists. Then we had to cover everything like from L to R previously, and then this new edge should go to R plus 1, and then this new subtree ends at X. And so now we have like this new incomplete tree from L to X, and we constructed it by choosing an incomplete tree from L to R, and then a tree from R plus 1 to X, but we also must have the edge from L to R plus 1. Pum, pum, pum. Let me try to turn off stream, reduce the resolution, and turn it on again. Hopefully it will be better now. I reduced the resolution, reduced the frames per second. So hopefully it shouldn't be that laggy now. Please send some nice reaction if the stream is working and not lagging. All right. What was the definition of T? So TLR is so it is like it connects to building a tree, like a subtree that is rooted in L and covers a segment of vertices with indices from L to R, inclusive. We don't yet know like what it is exactly, like how it is defined. So for now, let's say that it is just number of ways to build such a subtree. So number of ways to choose subtree rooted in L that covers vertices from L to R. It is not the same as number of ways to remove a set of edges, but we want to understand the structure of the GP first, and then what exactly are we counting and where. So if we just counting the trees, then the update is draw another edge from root to like the next new sun. We must have this edge. Everything before, like strictly before this vertex, must be covered before. So we had this like incomplete subtree covering from L to R, and we have chosen subtree with root in R plus 1 that goes up to x, and we added this subtree and use this edge from L to R plus 1 to add it. Right. It might look like it's cubic, as like most segment subsegment DPs that work somehow like that. Look, we're choosing three indices, right? Like L, R, and X. But actually, our transitions correspond to edges, so we can like fix an edge and make transition corresponding to that edge. So we're choosing edge and this value of x. So the number of transitions is actually of n times m. So it would be fast enough. The problem is we are not counting what we need to count actually. We're counting something else, number of subtrees. So let's now understand how to choose what the DP state corresponds to. We can now count what we need, the number of sets of edges to remove. And so my way was to say that we will consider edges to be removed that are only like inside the segment LR. And all the edges that are not from L, like we are considering like down, like further down when we basically we're trying to remove every edge when we consider like this left end point of the edge as the root of the tree. And what edges we can remove and or not remove. I don't know, it's like is my internet that bad? I don't understand. Well, this is not going great. Every time you do something to fix the logs, they're fixed for like for a couple of minutes. Okay, cool. I should just like switch to OBS for uh, once every 2 minutes, and that would be great. Well, notify me when it goes down again. Right. So I was trying to explain uh, how do we count like sets of edges to remove, um, and said that we will consider the edges to remove when we consider in the root. Um, so okay, let's. So we have current root. Something is already covered. Then we are adding this new subtree. Um, and so like obviously we have to keep the edge. Well, I'm not saying anything right now because mm, YouTube was again saying that the stream has died. Um, I don't know. Is it working now? It, it says it's good. Yeah, I'm very sorry about this whole thing. Like I'm this is my first time streaming in like a year, and it looks like it's not working. Okay, we'll try to move on. We have a root. We have a new edge that we are edging. This is a segment that will be covered in the new subtree. If we stop now, what will happen with the edges that go past this point? Well, I say that we must remove all of them, because otherwise, like, we are stopping means that this from this vertex we shouldn't visit more than this. And it's down again. Amazing. Just amazing. Okay, so I set very low resolution and very low FPS. Maybe, just maybe, it will work. Send thumbs up or something if you can see and hear a blurry me with very low resolution and very low FPS. Okay. Let's try to finish this problem. It's cursed, but well, right now bitrate is like 1000 kbps. Although I have no idea what those numbers are. Well, when I started, it was like 7,000, and YouTube set lower to 2,500. Then I did that, and YouTube said make it 1,000. Let's. Well, I think it hasn't stopped, hasn't lagged since I changed settings the last time, so let's try to continue with these settings, and if it starts lagging, I will try to make it even lower. Right. Edit new subtree. And let's say we are stopping right now. So this will be our subtree, and then it will be hand to some new root and something. So if we have edges that go outside of this box, like to the right, then we must cut them, because otherwise when we were processing this vertex, we will go to the right. Like if we have an edge to the right, we will have to use it. They are not visited yet. We will try that edge and go to the right. So if we want to stop right now, we have to cut those edges. we have already decided on the edges that go here, because like we have taken calculated dp value like up to this point. So now we only need to decide, do you want to take edges that go to this subsegment? Obviously we need to take the first one because we want it in our tree, so we cannot delete it. What about the other edges? So if we have edge to some other vertex, well, then I say it doesn't matter if we have it or not. We will not use it in the tree because like everything here will be traversed when we do like DFS from the in this subtree. So when we go back from this subtree, return to our root and try to consider this edge, it will lead to an already visited vertex. So it doesn't matter if we have that edge or not, nothing will change. So when we do this transition, we can look at all the edges that lead to like the remaining of this segment, except the first vertex. So the first edge we must keep. All the other edges we may delete or not delete. So we just need to actually like multiply this by the 2 to the power of number of edges to this segment. So in this transition we also need to multiply 2 to the power of CNT, where CNT is the number of edges from this vertex to this segment, like from r plus 1 to x. And we can either like pre-calculate it somehow, like for example for every vertex we can pre-calculate like a prefix sum array for like how many edges we have to every prefix, and then take a summon segment in constant time, or just like when we are considering those transitions, we have fixed the edge from L to R plus 1, then we are iterating over X, and we can maintain a pointer to like the next edge. When X reaches it, we will increase CNT by 1 and like maintain this power of 2. So we can still do this dp in of n times m, which is fast enough. Okay, the main question, is the stream still working? Was there any lags during those 5 minutes? If no, then it looks like we are finally through problem D. Although I'm assuming that nobody understand anything because the explanation was stopped every other minute. It's working. Okay. Are there any questions about problem D? Can I do a fast recap? Well, I can try. So our main idea is that our DFS order is like sorted, which means that like a subtree of the DFS tree is a subsegment in the DFS order, but our DFS order is sorted, so it means that every subtree is just a segment of vertices. And then we want to do a subsegment DP that counts the number of ways to remove some set of edges if we only consider edges that are fully lying on the segment from L to R, such that if we only consider those edges from L to R, only the non-removed ones, and do a DFS from L, then we will visit the segment from L to R in the correct order. And then the transition is in this DP is to so we're taking like this subtree, and then we're adding a new edge from the root to the next vertex in order. So if that was from L to R, then the next vertex in order is R plus 1, and its subtree will cover like vertices from R plus 1 to something. So we have L, R, X. Those are our three parameters of the transition. But it is not n cube, it is actually nm, because we must have edge L R plus 1, so we can say that we're iterating like over the edge we are adding and x. So that's m times n. When we do the transition, we need to choose like what we did here, what we did here, and now what we do for the edges between those parts. But then like all the edges not from the root to the right thing we must delete, because that would like if we have an edge like this, it means that when we were here, when we were doing DFS here, we must have traversed that edge, but we didn't, so there wasn't such an edge, so we must delete it. And for the edges from the root, we must keep the edge that we are using, but all the other edges we might have, we might not have, it doesn't matter, it still works. So we will multiply the number of ways by 2 to the power of those number of edges. And that number we can like either pre-calculate some prefix sums to calculate fast, or when we are iterating over x, maintain the number of edges, or just 2 to the power of that number of edges, to make transitions in constant time. And this DP will work in O of nm, which is fast enough. Sounds good? Any questions? How are you calculating CNT exactly? So CNT is the number of edges from L to the segment. So like this is well, if we are considering edge from L to R plus 1, then like from R plus 2 to X, we want to count the number of edges from L to this segment. So I did it the following way. At first I sorted all the edges from L, and also like I only store edges to the right. So I have my edges from L sorted. Now I consider them one by one from left to right. And when I consider this edge, I will then iterate over x. So my segment on which I need to count the number of edges, it starts empty. And then when I will increase x, it will increase. So I can maintain a pointer to the next edge that will fall into that segment because they're sorted. And when x reaches the next endpoint of the edge, I increase CNT by 1. So I like when I iterate over x, which is like this endpoint of the where this subtree will end, I am also maintaining a pointer. So if I have this L, this is the edge I'm considering right now, and I have more edges. So when I move in X, when it reaches this point, I'm like, okay, I have a new edge. I increase CNT by 1 and move the pointer to the next edge. When I will reach the next edge, I will again increase CNT by 1 and move the pointer, and so on. Is that clear? Okay. We can finally move on from this problem to problem E. In problem E, we had a connected graph, which was big, 200,000 or something. Every edge is either red or blue. We're saying that a word that consists of red, a sequence of colors red and blue, is good if there exists a walk from vertex 1 that traverses the edges of corresponding colors. Walk from 1 that uses colors in order given by the string. Then we say that the number k is good if every string of length k is good, and we want to find the smallest k such that it is not good, such that there exists not a good string. So first idea is that we can kind of try to emulate the process. How would that smallest counter test look like? So we have some string, let's say it's blue, red, blue, red, red, blue, blue. So let's say that this is our smallest counter case. So we start at vertex 1, then we have some blue edges, and we have some red edges. Since our first symbol is blue, then we must traverse one of those edges. We can even try to say, okay, let's use this edge. Although technically we don't have to make that choice right away. For now we only consider that the string starts with B, so we have to use one of those edges we don't have to make this choice right away. We can kind of like say that we non-deterministically go and like maintain a set of vertices that are available right now, but like that is a like nice thing to think about, but like we definitely cannot implement that. Well, not definitely, but we won't. So let's say that we are moving to this vertex. Then from this vertex we like we can look at the end of that string, and from that vertex this string must be like not viable, not good. Right, so we continue going. So now we need to choose a red edge, then a blue edge, then a red edge. So let's draw some sequence. Blue, then red. But then we want to use red edge again. And we definitely know that from this vertex there is a red edge going back. And I state that, well, this is kind of dumb for our attempt to construct a smallest bad string, because like if we arrive at some vertex by like having eaten a prefix of this string, then that suffix, the remaining suffix, must be a bad string like for the vertex that that we are standing right now in. And clearly it should be like the smallest bad string, right? But then like we traverse red edge, and then we can traverse red edge back. That doesn't make any sense. Like we certainly can stay in this vertex, but now we're trying to get a smaller counter test. So if this actually is a counter test, then cutting those two R's is a better counter test. Although, actually, I don't know if it's true. When I solved the problem during the contest, I kind of just believed in that. But now I'm not sure. Like, we can eliminate vertices from which there are no red edges, and then eliminate something else. Yeah, I think some smarter argument is needed here. Like, we need to consider like going back further. Like, if there is an odd number of red edges, then we can decrease it to 1. If there are even number of edges, we can remove all of them and like continue collapsing it. That works. Like we will have to return to vertex number 1, and like maybe there are more vertices available, but also it is not the minimal counter test. So what I'm trying to prove is that in the minimum counter test, the characters must be alternating. But my proof during the contest was wrong. So you can prove something easier. I'd love to hear what what exactly is the easier thing to prove. If there is a pass, alternating pass, blue red, and so on, and the same starting from red, both lengths k minus 1, then the answer is at least k. Yeah, that is okay, sure. Thanks. Yeah, okay, that's good. Yeah. So k is the smallest number such that there is no alternating path starting with some color from vertex 1. If there is no such path, then obviously we have constructed a counterexample. If there are such walks for both starting colors, it means that we are kind of like have blue red in this direction and red blue in this direction, and so like those are like k edges, and so each time we need to traverse some color, we always have an opportunity to do so while staying on this path until we reach one of the endpoints, so we can make at least k moves for any string. Okay, great. Yeah, thanks. That is actually simpler. So what I tried to prove, and my viewer actually explained to me how to prove, is that if there is a minimum counterexample, it will be an alternating string. So now we want to understand what is the minimum length of that alternating string. To do that, we will construct a different graph. It will have 2n vertices, and it will be directed. So our 2n vertices, each vertex of the initial graph will correspond to 2 vertices in the new graph. And so if we had vertex v, we will create basically v blue and v red. And that will be like, I'm standing in vertex v and I want to use color blue next for this vertex, and I'm standing in vertex v and I want to use color red next. So what are the edges in our graph? So let's say we had a blue edge vu. Then I can use this edge only if like I'm in a vertex that wants to use blue edge next, right? So if I'm in VB, then there is a directed edge, and if I traverse this edge, I will be in vertex U, but the next edge I want to use is of color red. So I create this directed edge. And symmetrically, if I was in UB, then I can move to VR. So we're building a new directed graph on 2n vertices. Each vertex of the original graph corresponds to 2 vertices, V blue and V red. And if we had a blue edge, VU, we create 2 directed edges like this. And if we had a red edge, similarly, but like VR to UB and UR to VB. So now in this new directed graph, we can choose where we start in like vertex 1 and blue and or vertex 1 and red. But then on this graph, we just move through the directed edges. So we want to find what is like for those 2 starting vertices, what is the longest directed path one can traverse. And you can do it in many different ways. I guess one simple way would be to say, so for fixed start, we can just run DFS from that start to see what vertices are reachable, remove unreachable vertices. If we have a directed cycle on reachable vertices, then obviously we can run infinitely, right? Like if we can reach a directed cycle, then we can run infinitely on, like reach the cycle and then run infinitely on it. If we cannot reach a cycle, it means that on the reachable vertices, our graph is acyclic, so it's a directed acyclic graph, and we can find the longest path from every vertex using a DP on DAG. So that's one way. I did it a bit differently. Well, it's basically the same, but I didn't I actually check which vertices are reachable, then like build a topological ordering on them and run DP. Instead, what we are doing here is basically retroanalysis. Like it is kind of similar to how games work. Like if we have a vertex and some directed edges from it, the answer for this vertex is maximum over answers for all those vertices plus 1. Because like basically we are choosing to traverse a longest walk from this vertex. We want to like go to one of the vertices we can from our current, and which one we choose? Well, the one from which we can continue the longest walk. So the answer is maximum of those plus 1. And if we like go back, kind of like, what are the vertices for which the answer is 0? Well, those are the vertices from which there are no edges. What are the vertices where the answer is 1? Those are the vertices from which all the edges go to the vertices with answer 0. What are the vertices with answer 2? Well, those are the vertices from which the edges go only to like answers 0 or 1, and there is at least 1, 1. So we haven't decided yet. So it's very similar to doing retroanalysis. And yeah, that retroanalysis is like similar to BFS, but well, it's slightly harder than BFS, but it is also graph traversal with a queue, but you need to maintain the number of outgoing edges you haven't processed yet. So that works in linear time. There was a question. Can you do a fast recap of the graph construction? So the idea is that we like we're saying that our state is the vertex where I am and what color I want to use next. And since the color alternate, if I'm staying in V and want to use blue edge next, then like for a blue edge VU in the graph, I can go to to the state I'm in vertex U and I want to use red edge next. And this way our graph is directed now. So like the state is where I'm staying and what is the next color I want to use. Then from that state, I can look at all the edges of the color I want to use from that vertex, and when I use that edge, I like go to the other endpoint but flip the color. Does that answer the question? So you're basically splitting each node into two and distribute the edges of it on the two nodes depending on the color. Yes, and I also making the edges directed because well, they're directed now. Okay, great. I'm assuming there are no more viewers, so if you understand everything, then we can move on. Okay, problem F. Problem F is nice. So we are defining like function of array as well, basically it's max of the set of sums as such that S is the sum in some subset of elements. So for an array, we are creating a set of all sums that can be chosen, like a sum of subsequence. And then in that set, we're finding, well, not in that set, but for that set, we're finding minimum excluded, so the smallest value which is not present in that set. Or in terms of original array, it's the smallest number that cannot be represented as the sum of some subsequence. And max of all subset sums, yes, exactly. We are given an array of lengths up to 200,000, I think. The elements are up to 10 to the ninth. And we want to calculate the sum of values of f over all subsegments of this array. So we're calculating sum of f of L plus 1 R. So that's what we want to find. Okay, so first we need to understand how to calculate f for a given array. It is a well-known problem, and one way to understand it is to say, well, obviously the order of elements is not important, so let's say we sort them. I was able to solve for each prefix using bit set of size 10 to the 9th, or like it's actually more than that, right? And times 10 to the 9th. So no, I don't think you can do that. I mean, you can, but it is not. It will not lead to a solution, like to a full solution. So if the limitations were like add up to 100 and AI also up to 100, then sure, just like do what is written and it'll be great. Isn't the max always small? No, the max is not always small, because like the size of the set is very big, like 2 to the power of m, and like if your numbers are just powers of 2, so only 30 numbers are needed to cover everything like up to 2 to the power of 30. Like, every number is representable as a sum of powers of 2. Like every number smaller than 2 to the power of 30 is representable as a sum of powers of 2 smaller than 30. So no, the max is not always small. I'll go back to explaining my solution. So we sort the values. If all the values are bigger than 1, then 1 is not representable as a sum, because sum of nothing is 0, but if we take at least one element, then it's already strictly greater than 1, so it's bad. If a1 is at least 2, then f is 1. And bit set of size around, well, yeah, but bit set of size around a billion is already way too much. Okay, so now we consider that a1 is 1. Then 0 and 1 is representable. If a2 is at least 3, then like everything else is also at least 3, then A2 is not representable because well, we cannot take big values, but small values are not enough to represent 2. So now A2 is at most 2, and if A2 is 1, then we can represent 0, 1, or 2, and if A2 is 2, then we can represent 0, 1, 2, 3. So we can represent everything from 0 to A1 plus A2. And we can notice similarities here. So at every step, we can represent something up to big X. Initially, it is 0. We can represent 0. We cannot represent anything else. We don't have elements yet. If the element is strictly greater than X plus 1, then X plus 1 is not representable. Because with smaller elements, we can only get up to X, and bigger elements are too big. Otherwise, if it is at most X plus 1, then so we could represent from 0 to X inclusive. And we have our AI somewhere, which is well, up to like this X plus 1. So without AI, we could represent this. With AI, we can represent like AI plus something that is between 0 and X. And so now we can see that the set of representable values is everything from 0 to AI plus X, and X is just the sum of all numbers. So basically, if we sort the array, we will like maintain the sum on prefix. Initially it is 0, then we run to the right, and if the new value is strictly greater than sum of previous elements plus 1, then sum of previous elements plus 1 is not representable, and it is the smallest not representable value. Otherwise, we add this new element to the sum and continue. So the answer, the function f, will be sk plus 1, where k is so sk is the sum on prefix of size k, and k is the smallest index such that sk plus 1 is strictly smaller than the next element. Or if k is m, then the next element doesn't exist, so we kind of can say that it's infinity. And everything from 0 to the sum of array is representable, but sum plus 1 is obviously not representable. Okay, so that's how we can calculate f. But that doesn't seem like helpful enough. I mean, it is helpful. We now can have like a polynomial solution without any knapsacks. So if we want to calculate f, we need to sort the array and then do this linear search. But like, it seems that we need a linear search. How can we try to make it faster? Well, there is another well-known idea of how you can do those checks faster, and the idea is the following. basically um, we want to increase the sum fast. So we are moving through the like sorted values, maintaining the sum. Uh, if the next value is bigger than the sum plus 1, then we stop. Um, but if it is a bit smaller, then the sum will increase like almost 2 times. And that cannot happen very often. Um, but on the other hand, we can have a lot of small elements, and like then the sum will not increase fast enough. But we can try to like skip fast to the next element that is like potentially is bad. So for example, if we just want to calculate f once, um, well, we will need like to calculate prefix sums or something, but we're doing for subsegments, but we need sorted order. So like it is not good enough yet, but like assume that we have sorted order, and we calculate prefix sums. Then we can emulate this process faster. How do we do that? So let's say we are staying at some position, we have sk. Then all the values that are not greater than sk plus 1, we know that they're good. So we can like lower bound try to find the next place that like technically can break us. Then everything here we can just skip and calculate the sum. Let's say it is pre-calculated, we just have prefix sums. Then we arrive here and just check if the condition is broken. If it is broken, then we stop. If it is not broken, then we will move on by 1. But this value we chose such that it is greater than sk. So after we add it, after we move 1 to the right, we know that our sum is now at least 2 times sk. So in like we did one big jump and then one small step, and we know that after that our sum is at least twice as big as it was before, so we cannot have a lot of such steps. Okay, there is another message in chat. If we fix the left border and state the right border at the same index, start to move by 1, the max will only increase. That is true, but it is well, we are not there yet. We're still just working with one array, trying to understand how to find this max fast, and like what are the properties of that process. So like here we have a process, but it is linear. Now we made it faster than linear, and it is actually like log like like the sum of the numbers times log n, because we need lower bound. So the number of steps will be bounded by this, because each time we multiply the sum by 2 at least, so we cannot have more than log c steps. And for each step we need a lower bound. But to do it, we actually needed like a sorted order, and prefix sums on that sorted order, which sounds bad. Like we cannot just like take every segment and find sorted order and calculate prefix sums for that sorted order, because, well, yeah, what we would like to do is to fix left border and then try to like move right border and calculate the sum of all answers somehow. But that is not easy, and with our current way of calculating f, not really possible. So we need an even better way. And like the worst thing about our current approach is that we need a sorted order. The fact that we are doing jumps and there are a small number of jumps, that's great. But we need a sorted order to do this. We can eliminate the need for the sorted order and instead have a bit weaker thing, but the one that is easier to maintain when we change something. So the idea is to split all the values into buckets by like their highest bit. So we will have bucket of just ones, then 2, 3 in the same bucket, then from 4 to 7, from 8 to 15, and so on. So every bucket starts with like 2 to the power of k and ends on 2 to the power of k plus 1 minus 1. And then the next bucket starts with 2 to the power of k plus 1. And then I state that for each bucket, we are interested in the smallest value in the bucket and the sum of the values in the bucket. So basically, it is like a poor man's sorting. We separated the elements into small number of buckets. The buckets are sorted. Then we want to like emulate going through the sorted order and doing our algorithm. The idea is that basically the only place our algorithm can break, like this can happen, is on the minimum in some bucket. By that, well, we are like going, well, in this case, we're going up. And when we are considering this minimum, we have already summed up everything in the lower buckets. It can break now, but if it doesn't, it means that this minimum. So let's say, okay, our minimum was in the bucket that correspond to 2 to the power of k. And our previous sum, s plus 1, was at least minimum. So when we have a new sum, it will be old sum plus minimum. And old sum is at least minimum minus 1. So that is at least 2 times min minus 1. But minimum is at least 2 to the power of k. So this is at least 2 times 2 to the power of k minus 1, which is like exactly where our bucket ends. So it's 2 to the power of k plus 1 minus 1. So after we process the minimum value in the bucket, our sum is already enough to eat up everything in that bucket. So our algorithm cannot break right now. So we just eat up all the values, which is done by just adding the sum to our current sum. So now if we have those information about the buckets, for each bucket we have minimum and sum. Oh yeah, some of the writing is behind. Well, there is nothing interesting there. 2 to the power of k plus 1 minus 1. Uh, so if we have the information about buckets, uh, for each bucket, it might be empty, and if it is not empty, then we want to know the minimum and the sum in that bucket. Now we can emulate our algorithm for finding f actually in just logarithm. We don't need lower bounds anymore because we just process buckets one by one, and each bucket is processed by, like, we have the current sum, we compare current sum plus one with minimum. If minimum is strictly greater, then we stop and current sum plus one is the answer. Otherwise, saying, okay, we can eat up all that bucket, just add the sum in this bucket to our current sum and proceed further to the next bucket. The number of buckets is O of log C, or just log C. So we can calculate f in log C if we have that information about buckets. Is that clear? We now have a very good algorithm for calculating f. Now we will use it to calculate the answer that we want to find, even faster than just n squared. Can you repeat why we can eat up all the bucket? So when we arrive at the start of the bucket, we have some current sum. I called it s here. Compare it to minimum. If s plus 1 is strictly smaller than minimum, that's when we stop the algorithm, right? So we just find that s plus 1 is not representable. So if that happened, then we stop the algorithm, we found the answer. If it is not true, so s plus 1 is greater or equal than the minimum, then I'm saying that after we add minimum to the sum is already big enough, like it is at least the upper bound of the corresponding bucket. Like this new sum is old sum plus minimum, which is at least 2 times minimum minus 1. Minimum was in the bucket, so it is at least 2 to the power of k. So our bucket is from 2 to the power of k inclusive to 2 to the power of k plus 1 not inclusive. So the minimum was at least 2 to the power of k. So our new sum is at least 2 times 2 to the power of k minus 1, which is equal to 2 to the power of k plus 1 minus 1, which is exactly the higher bound of our bucket. So our sum is bigger than all the elements in the bucket. So we will not stop at them. So we can just add them up to the sum. Okay, great. So we now have this algorithm. We will try to solve the problem. I will erase pretty much everything. So I will keep the problem statement, and I will keep those vertical buckets just to remind. Okay, so now, yeah, we are fixing left border and want to sum up the answers for all the right borders. We will need to pre-calculate some things, like some data structures on the array, but for all intents and purposes, we just solving one left border in log square. So we can just assume that we started at the beginning of the array. Left border is fixed. Everything before that left border doesn't exist for us right now. So what happens when we process right borders? Yeah, as you correctly said, like when we move the right border to the right, when we add new elements to the set, obviously the set of sums can only also get new elements. So the answer can only increase. That also means that the number of bucket at which we will stop will only increase. So for some right borders, we will stop at bucket 1. Then for some, we will stop at bucket 2, 3, and so on. And finally, 30. Bucket 30 is no, bucket 31 is empty. Well, depends on how you number them, but yeah, bucket that should contain numbers that are greater than 2 to the power of 30 is empty, and therefore like there are just no elements there. We just stop. We summed up everything. So what I want to do now is I want to find those borders. If I find those borders, then I'm basically done. If I know that I'm stopping at bucket number 3, for example, it just means that the answer for right border, like inside this group, is the sum of all numbers on that segment that fall in the first 2 buckets. And then we stop on the third bucket, which means that we stop like at the first element of the bucket. So we don't add anything. So if we stop at bucket k, the answer is just sum of numbers from the segment such that x is smaller than 2 to the power. And we can just calculate that easily because k is just up to 31. So for every k, we can just ignore numbers that are bigger than 2 to the power of k. On those numbers, just calculate prefix sums, and then we need to so the answer for this fixed left border and this right border is prefix sum here minus prefix sum here. So we need to take sum of prefix sums here minus prefix sum here multiplied by the length of the segment. Calculate prefix sum of the prefix sums and you will be done. So our goal now is to find the borders of those zones where we change at which bucket we stop. And we will find them one by one. So we start with on which segments we will stop at bucket 1. Find this place, then from this place on which right segment right borders we will stop at bucket 2. Find this, and so on. So let's say we have something. So here was like the last right border where we stop at bucket k minus 1. And we now want to find like where this ends. Where will be the groups that stops at buckets k. We can do it with binary search. Because as we said, the sync only increases. So we can try to fix right border and ask ourselves, will we stop at bucket k when the right border is here? How to do that? Well, we need to understand what like the information about our buckets. So this is our bucket k. This is smaller buckets. We already know that we don't stop at bucket k minus 1. So from here we only need like total sum. And from here we need the minimum. Aren't the buckets changing as we move r? Like the values of buckets are changing, but the buckets themselves, like they are always defined as from 2 to the power of k to 2 to the power of k plus 1, not inclusive. But the values are changed. The sum and the minimum, they are changed. Okay? All right. So to answer like will we stop at bucket k, we need to know the sum on this segment of the values that are like smaller than 2 to the power of k, and the minimum like in this bucket, but technically it's fine to say just the minimum over all the values that are like at least 2 to the power of k. If this bucket is empty, like it's fine if we just take the minimum over all the values that we have greater. That will be like the next value we encounter after the first k minus 1 buckets. Right. So we need to calculate minimum over big values and sum over small values. But like what is big and small only depends on k. So for every k we can pre-calculate some data structures that we need. For a fixed k, we need to calculate sum of small values. That's just prefix sums if we replace big values by zeros. And we need minimum over big values. Now we replace small values by infinities and create some data structures that allows us to calculate minimum. For example, sparse table. So for this, prefix sums on small and sparse table or like any range minimum query data structure on big. And that's pretty much it. So now let's see. Our complexity is for fixed left border. We iterate over k from 1 to 31. So that's log c. And we do a binary search to find this border. With log n. Our queries to data structures are just prefix sums and sparse tables, so those are of 1. But we also need to construct the data structures. For prefix sums, it's just, well, we need log C versions of our data structures. So like one sparse table for every k and one prefix sum for every k. So it's log C times of n, and here it's log C times n log n. And like overall it's n log c log n, which is good enough. There is a small issue that this is n log n log c memory, but we actually don't need it all at once. Instead of like iterating over L and like solving every group, finding every group, doing binary search. If we do that, then yeah, we need to construct all the data structures in the beginning and then use them. But instead, we can iterate over k, and for every L, find the next border. Then remember where that border was. For every L, then throw away the data structures we used for the previous k, find the like build the new data structures, and process k plus 1 for every left border. Then like the time is still the same, but we don't store all the data structures at once, so it's just n log n memory. And that's time complexity. That's it. Problem F. Can you quickly go over the implementation? Like I don't know what exactly. Like, I mean, I explained how to save memory. I can show my code, but I think you will be able to see it later, anyways. I don't know. I can show it here, sure. Okay, so that's just multitest. Solve. Just read the array. Initiate the borders for every left border. Like we didn't find anything yet. Then iterate over all k. Solve k. It will increase the answer and move the borders. Can I increase? Let's see. Can I? Is that better? Okay, I think I can do one more. I mean, I think that's okay. that still fits on the screen. Okay, so read the array, initiate borders for each left border where we are standing. Answer is 0. Then we iterating over k, calling solve k. I'll just print the answer. Solve k. So we building our data structures. So we have prefix sums and the sparse table. Going over elements. If the element is small, then we put it in the prefix sums. So we calculating prefix sums. If the element is big, then it is 0 for sums. So we like prefix sum is just the previous one. Otherwise, add AI. If the element is big, then so for sparse, if the element is small, then it's inf. Otherwise, we put it in sparse. Then we build the sparse table, and also I have this pref, which is to calculate for calculating the answer. I have prefix sums of prefix sums, and then for every left border, this is our previously reached position. n+1 cannot be reached. Doing binary search. Calculating the sum of small values, getting the minimum of the big values. If the big value, if the minimum exists and the sum is big enough, then it's good. So I move the right border. Otherwise, I move the left border. Something. Okay, and now from this position to L is this is my group that will stop at K, and I'm calculating the answer. That's it. I know. Does it help? Okay. And we can move on to problem G. Thankfully, it won't be very long because I'm not sure if I can solve it. Like, I mean, I did something and it was fast enough, but I don't know if it's the intended solution. So in problem in problem G, we were given a grid n by m, and m up to 300. The values in the grid are integers up to 100,000. We're considering all the paths that go only left or down. We will sum up over all such paths the following thing. For the path, we're looking at the like some two positions on the path. Look at the values here, and if x times y is a perfect square, then we add to answer Fibonacci of square root of xy. and we want to calculate the answer. Okay, so answer is sum over all paths, sum over ways to choose 2 points, this thing. Obviously, we want to flip the order of summation and say that let's fix 2 points. If their product is not a square, then ignore. If it is a square, then we need to calculate the number of paths that go through both of those points. So fix 2 points. Shouldn't have used x and y here, but too late for that. So let's say that this value is a, this value is b. If a times b is a square, we need to add to answer Fibonacci of square root of ab multiplied by the number of paths. Number of paths is, well, should be easy and well known, and if you don't know, then you have like 0 chance of doing anything in this problem. So if we just count the number of paths that like from start to finish, it's binomial coefficient. I think it was written in the statement. And if we have 2 fixed points, well, that means that we want to take any path from start to the first point, and from the first to second, and from second to finish. So we need to have like x1 is at most x2 and y1 is at most y2, and then we multiply some binomial coefficients. This times x2 minus x1 plus y2 minus y1 x2 minus x1 and another like n minus 1 minus x2 plus m minus 1 minus y2 choose n minus 1 minus x2. Okay, so that's the number of paths, so that's what we want to calculate. Okay, great. This is n to the fourth, and the limitations are not that big, right? I think tail was like 5 seconds. So if we just iterate over all the pairs and we can quickly check if like the product of those two numbers is a square and what is their Fibonacci, that would be like and choose 2 pairs, but actually it is even smaller because we have this condition, so it's actually like n plus 1 choose 2 multiplied by n plus 1 choose 2, so it's like 300 to the power of 4 divided by 4, which is not that much actually, but well, I hope that that doesn't pass, because otherwise that would be way too stupid. Because like there are some multiplications, modulo operations. I think it shouldn't be fast enough, but it shouldn't be too far from passing. Maybe like 3-4 times slower than passing. But we don't need to optimize by a lot, and like we can try to do something a bit smarter, and like it will be much more difficult, but not much faster. I don't know if you can do something much faster. and like I was thinking for a long time that like how to do it much faster, and couldn't come up with anything. And then I was like, okay, I don't need to do it much faster. Just let's just write something. Okay, so there is like a kind of known problem when there isn't this like Fibonacci thing, just like count the number of paths such that those 2 points are of the same color. Like for every point in the matrix is given a color, and like you need to sum up the sum overall paths, sum overall points. Is it true that they're of the same color? And then you switch the ordering like this, and for every 2 points of the same color, you need to sum up like the number of paths that go through those 2 points at the same time. And for that problem, like if there is no Fibonacci, well, technically we're not given colors, but we can show that it is the same. So if we don't multiply by Fibonacci, we can do a kind of squared edge composition. So if the size of like if the number of points of the given color is small, just iterate over all pairs and add it to answer. Let's say that we had like C1, C2, CK number, like those are the sizes of the components. Then the sum of Ci is Nm. And for small components, we can afford to spend squares. So like if Ci is smaller than something, just do it in a stupid way. Iterate over all pairs and multiply those binomial coefficients. Do stupid of Ci square. So if we sum it up over all small Ci, like this Ci square is at most Ci times b, then we so sum over all small of Ci square will be sum over all small Ci times b. Then we can take b out of the summation, b times O of Ci, and this is bounded by Nm. So this is O of b times the area of the square. But if Ci is big, we will solve this color in O of Nm, basically by like doing dp on this matrix, basically doing what is written in the statement. So if we have like big number of points, we can say okay, so for every point, like it can be a start. So if it is a start, like we multiply by x plus y, choose x. So like we okay, what do we need to do? We need to calculate the number of ways to choose 2 points, and then choose like those 3 parts of path. But like if this point is a start, then like this number is this binomial coefficient, number of paths here is like this binomial coefficient. But when we choose this point, we can like basically this part of the path we can walk through it and calculate like DP. So we will calculate DP, like what is the number of ways to reach this midpoint on the path. And it will be, so we initialize for every start with this binomial coefficient and then push it in of nm in that direction. So to reach this point, we either start there, or we come from the left, or we come from top. So we can do this DP in O of NM. So we can process one color in O of NM. And if we do it only for the colors that we have a lot of, so that are greater than b, it means that we have no more than nm divided by b such colors. So no more than this time number of times we do dp in nm. So this is of area squared divided by b, and if we choose b to be like square root of area, then both of those things will be of nm times square root of nm. Is that understandable? No, that will be behind me again. Can I move it? I can move it like this. So the DP is DP NM3. Well, you can do it like this, but you don't have to. You can only do it for like the middle part and then iterate over all the endpoints and like sum up the answers. Yeah, you can do DP NM3, but you don't have to. You can only solve the middle part of the path like this. So for every point in the grid, you will calculate like so the grid, and for this point, those are the starts. You will calculate how many ways there are to like go through some start and arrive at this point. And then when you know that for every point in the grid, you just iterate over all the possible ends, and like take the DP calculated there, multiply by this binomial coefficient, like the number of ways to end from that endpoint. Is that understandable? Okay. But our problem is harder because we have this Fibonacci thing. So first, how will you make sure that you passed by one of the start? I only start at the like for each starting point. I initialize DP there as the number of ways to reach it, and then like with those initial values, I push them down with DP. The number of ways to reach is just like this first binomial coefficient. Okay, now we will go back to our problem. So Well, first of all, AB is a perfect square. I said that. Come on, why do I want to write square with an E here? I said that it is the same as colors, which is not obvious, but it is true. For every number, we can represent it as a square of something multiplied by the number that is not divisible by any square other than 1. Basically, if we look at the prime factorization, if it is divisible by some square of a prime, we put that prime in this part and remove it from the square free part. So every number is uniquely representable as a square free part multiplied by a square of everything that is remaining. Color is mask of parities of the exponents of the primes. Yeah, that's it. Yes. So each number is uniquely representable as a square free part. And some square. And yeah, AB is a square if and only if their square free parts are the same. Well, we can just see that when we multiply them, so those are obviously squares, and those when multiply also must be a square, but each one of them can have each prime at most once. So in the product, each prime can appear like 0, 1, or 2 times. So for it to be a square, it must be either 0 or 2, which means that they must have the same set of primes. Okay, so AB is a square if and only if their square free parts are the same. So now we can group our points by their square free parts. We can pre-calculate with like a sieve or something for every number its representation into square and square free part. Then group the positions by square free part. So now for the points we are considering, they have the same square free part. And the square root of this thing will be like square root of this, which is just a1, square root of this, which is b1, and square root of a2, b2, which is just a2 because they're the same. So we will need to take Fibonacci of a1 times a2 times b1 when we consider them. Yeah, now we can consider every square free part separately for a fixed. So this is fixed now, but we still have a1 and b1, so like other parts of representation, which are also like important because they appear here, and like I don't see a way, I don't think it is possible to use that it is Fibonacci of that, because like if it was the sum, then yeah, maybe, but product of indices, like that doesn't make any sense. So we kind of still need to, so we have those groups. So this is now fixed, and we have groups by square part. um, we still can just like iterate over all pairs and calculate the value. So from our like square root solution, uh, the part that works in number in square of number of points still works great. Um, but if we want to do the faster thing, like if the group is big, we wanted to do this GP, but we cannot do it when we have different groups. But if we fix one of those things, then we can calculate DP for it. Like, actually, we will calculate two DPs when it's the first point and the second. And then for all the other points, we can take answer from that DP. So if we have groups like by this thing, C2, if we have groups like this, we can choose some of them, like the big ones. So those are big, those are small. For big ones, we will calculate DP in NM, and then for every so we will take a big group, calculate the DP, so we fix like that one of the chosen points will be from that big group. Then we iterate over all other points and just like look at the calculated value in DP and calculate the answer with it. This like number of points is also bounded by NM, so we can process one big group in of NM. And then for the small groups, we will process them like in a stupid way. Just take sum of CI square, and we have those points. Take a pair of them, calculate their contribution to the answer. Now I state that like with some I state that that's what I wrote and it passes. And I think in my code that passes, small is like at most 30 or something. So here we have like some of those groups square, which like doesn't seem very good. Like the square T solution worked fast because it was like sum of squares instead of sum of all the sizes square. Like sum of all the sizes square is bad. But the thing is that this K is not very big. What is K? K is the number of different groups by the square for a fixed square free part. But that means that those number of groups is bounded by square root of 10 to the fifth. And like I think from here we can show like something relatively fine. Like I think it should be like with a well chosen bound, the complexity should be like nm squared divided by 10 to the fifth fourth root. Like this square root, it will be square rooted again, like from the balance in the square root decomposition. So that's what I wrote, and it passes. that's all I can say about this problem. I'm pretty sure that it's like okay complexity, but only because like stupid solution is almost okay complexity. Can you make any use of the fact that square AB is at most? Well, yeah, I guess that's what I was doing. Or like this square root. Well, that's just like I can pre-calculate all the Fibonacci's. Okay, so I get that it is not like very proven solution. Like I explained the motivation. I explained how to write stupid area squared, and like why this should be slightly faster, and it is fast enough to pass. I can also see that some big fan of mine wants me to explain ABCD. I did it like 2 hours ago, probably more. So you can watch like the start of the stream. I think it is available right now. Yeah, the question was your question was something ago. Yeah, yeah. Okay, so I think we are finished. Do you have any more questions? Are you planning on doing the next educational round? I don't know. I mean, Cheyenne probably is planning. He didn't ask me to do it, so it wasn't in my plans. So I think there is a stream planned on Cheyenne channel, which is where we are now. But well, at least he didn't ask me to do it, so I don't think that I will be doing it. I meant on your channel, I remember you used to record screencasts. Yeah, true, but well, first of all, I recently updated macOS, and the tool I use for screencasting kinda broke. Not really, but it freezes the camera, and it's not very nice. Uh, and also, I have been doing long contests for the last 3 days, so I think educational is tomorrow, and I want to take a break. That's too much. I did team 5 hour contests yesterday and the day before, and today I participated in at Coder Grant and then in this Repovive contest. So it's like 16 hours of contests in 3 days plus 3 hours stream right now. So like if I'm not getting paid, I need to take a break. All right. Thank you so much for sticking with me. It's much nicer when there is at least somebody listening and asking questions, because like I can uh, I can see if like my explanation was at least understandable for at least one person. So thank you very much. Thanks for watching. For maybe future viewers. Bye.